So, hello students, let's continue from our previous lecture on the numerical integration. We have seen that our Gauss quadrature method is developed in the space of -1 to +1. We have the sampling point locations and then the corresponding weight factors, and now we have a new class of finite elements which are called as isoparametric elements, that give us an advantage that whatever may be the type of element, we can do the integration and we can control the accuracy of our integration. Either we can get the exact value or slightly under predict our integral value. And so the need for this is felt because our generalized coordinate method for deriving the shape functions has resulted in some quantities with polynomials, and we end up with a lot of integrals, whether it is stiffness matrix, the load vector due to the self weight, or due to the initial stresses and so on. And so we need some method for evaluating them, and when we have a irregular shaped elements, we cannot directly do the computations because we do not know exactly how to do the integrations. So we have one class of elements called as isoparametric elements that involve in converting any shape in the Cartesian coordinates to simple shape in the natural space. So any shape is converted into in the one-dimensional problems, we convert them into a straight line. So you take a curve and we convert them to a straight line of length 2 units, and then if you have any quadrilateral shape, we convert that into a square in the 2-dimensional problems, and that has an area of 4 units. Then a 3-dimensional object we can convert into a cube in the 3D problems and having a volume of 8 units, and then we can also convert them to triangles or some other shapes in the corresponding to the shape that we have in the Cartesian space. So here, so if you have a quadrilateral like this, an irregular quadrilateral, we can convert them into a regular shape of square having a length of 2 in each direction. Okay, and say a triangular shape like this, we can convert to an equilateral triangle. And in the isoparametric space, in the one-dimensional space, the length is 2, and in 2-dimensional area of 4, then in 3-dimensional space volume of 8. Okay, and so actually programming becomes very simple because now all our elements, the coordinates are going to vary from -1 to +1 in the case of quadrilaterals, and in the case of triangles they vary from 0 to 1. Okay, the triangles we will deal with them later, but now let us only look at the quadrilateral elements. And we are going to develop some mapping functions to map between the natural space or the isoparametric space to the Cartesian space. So the natural space is in terms of xi and eta, whereas the Cartesian space is in terms of x and y. Okay, this could be in 1-dimensional or 2-dimensional or 3-dimensional, and we are mapping x and y to xi and eta through some functions. And let us develop some mapping functions m1, m2, m3 and so on, and which are written in terms of xi and eta, so that we can map between Cartesian space and then the isoparametric space. And our mapping functions, they also have some properties similar to our shape functions. The mapping function mi evaluated at its own node, xi I and eta I is exactly equal to 1, and mapping function evaluated at some other node is 0, and the sum total of all the mapping functions is equal to 1. This is required for unique mapping. Unique mapping means for every point in the natural space, there should be only one point in the Cartesian space. For every xi and eta, there should be only one x and y. We cannot have 2 points. And what are the conditions for the unique mapping? So we need to have an element with all internal angles less than 180 degrees, and then if you have any intermediate nodes along any line, they should not be too far away from the center, like we have this middle third rule. Similarly, we have we place these nodes within the middle third, okay, and then and any internal angle more than 180 degrees could lead to non-unique mapping. And so if you have a very complicated shape, then what we do is we divide that the shape into smaller number of elements, larger number of elements, so that at lower level, at small element level, we may have unique mapping. So all the internal angles should be less than 180 degrees. So in this case, we can divide this into 2 elements, and then here also we may need a line. We can divide this into 4 elements, so that we get a unique mapping. Or sometimes we can exploit the nature of these elements for a special case, like say one element called crack tip element is developed by locating these intermediate points at 1/4 the distance. These are called as quarter points, and by locating these two very close to this point, we can simulate the stress singularity at this point. Okay, and so this particular one is specially used in the fracture mechanics problems to improve the solution accuracy, and we can see that if we have this, the stress at this point is very, very large, similar to our stress singularity. And now in these elements we have mapping functions for Cartesian coordinates x and y, and for interpolation for the field variables we have the shape functions, and our internal displacements u is n times ae, where n is the shape function matrix n1 0, n2 0, 0 n1 0, n2 and so on. Okay, and the n's are the shape functions which are written in terms of xi and eta, and if we use the same number of nodes for developing mapping and shape functions, we end up with the same functions for both mapping and then the shape functions, and m is exactly equal to n, and we call such elements as isoparametric elements. In most cases we will be using only isoparametric type of elements where our mapping and shape functions are the same, but in some cases we may have slight differences. So we have a subparametric element where our geometry is simple, like let us say you have a square shape. We just need the 4 corner points for representing that shape. We don't need more than that. So we can use mapping functions of a lower order, but let us say our displacements vary in a quadratic manner, then we need more number of points for describing the variation of the displacements. So we may use in this element all the 8 nodes for describing the variation of displacements. whereas we use only 4 nodes for describing the geometry. And so the mapping functions have a lower order variation compared to the shape functions, and so this element is called as a subparametric element. Actually we will come across the subparametric element later when we look at the infinite elements, but otherwise we will be mostly dealing with only the isoparametric elements. See, on the other side we have the superparametric element. The shape is very complicated, so you need a higher order of mapping functions, and if your variables are having a lower order of variation, we can just simply use these 4 corner points for our interpolating the field variables. In this case we call these as superparametric elements, and in our course we will be sorry, I think this should be subparametric elements. Our most of the course will be dealing with only the isoparametric elements, where we have the same mapping and shape functions. So let us try to derive the shape functions, isoparametric shape functions, and let us start with only one dimensional elements so that it is more easy for us to conceptualize. And let us consider 2 points, node 1 and node 2, at xi of +1 node 1 and xi of -1 node 2, x1 and x2, and x1 is greater than x2, and we can get the shape functions by different methods, by Lagrange method or the generalized coordinate method. Let us try to get our shape functions by the Lagrange method, and n1 of xi is the xi minus of -1, the xi minus the location at the other point, and that is -1, divided by the coordinate value at node 1 is 1, minus of the coordinate value at other node, that is -1, so that is 1 plus xi by 2. And similarly n2 of xi is xi -1 divided by -1 the coordinate at this point, minus of the coordinate at the other point, so that is 1 minus xi by 2. And these are the 2 shape functions that we get. n1 is 1 plus xi by 2 and n2 is 1 minus xi by 2, and the sum total of the 2 shape functions n1 plus n2 is 1, and in general we can write x as n1 x1 plus n2 x2, because our element is defined only in terms of -1 to +1, but in the Cartesian coordinates it is from x1 to x2. So we can write x as n1 x1 plus n2 x2, and our dou x by dou xi is dou n1 by dou x x1 plus dou n2 by dou x x2, and that is x1 minus x2 by 2, and this is positive only when x1 is greater than x2. Actually this is similar to our node numbering in the anti-clockwise direction. In fact this is anti-clockwise numbering, and the dou x by dou xi represents the scale factor, because in fact this is x1 minus x2 by 2. This itself is the scale factor, because in the natural space the length is 2, in the Cartesian space the length is x1 minus x2. Okay. So this dou x by dou xi is called as the Jacobian for 1D problem, and that is equal to L by 2, and if the nodes are numbered in the anti-clockwise direction, the Jacobian value is positive. And let us derive the same shape function by the generalized coordinate method. We can assume a polynomial, and because we have 2 nodes we need 2 terms in the polynomial, and we can only have first order polynomial because we have only 2 points. So, x of xi is a naught plus a1 xi. So, at node 1 xi is plus 1, x1 is a naught plus a1. At node 2 xi is minus 1, that is x2, that is a naught minus a1. So, by solving this, a naught is x1 plus x2 by 2 and a1 is x1 minus x2 by 2. So, once again we see that our n1 is 1 plus xi by 2 and n2 is 1 minus xi by 2. These are the same as what we got from the Lagrange method. And now let us introduce a third node. n1 is at xi of plus 1, n2 is at xi of minus 1 and the third node is introduced at xi of 0. So, actually the concept here is we need minimum 2 nodes for defining any line, and if you have a curved line then we require intermediate node, and that intermediate node is introduced at xi of 0, and once again this length is 2 and the nodes are at xi of minus 1, plus 1 and 0, and we can get the shape functions by the Lagrange method. See the shape function at 1 is xi minus of minus 1 times xi minus 0 divided by 1 minus of minus 1 and divided by 1 minus 0. Okay. So, this comes to xi of xi times 1 plus xi by 2. Similarly, n2 will be xi times xi minus 1 by 2 and n3 is xi minus of minus 1 multiplied by xi minus 1, okay, and divided by 0 of minus 1 and 0 of plus 1 minus of plus 1, and this comes to 1 minus xi square. So, these are the 3 shape functions that we have for the 3 node bar element: xi times 1 plus xi by 2 and xi times xi minus 1 by 2 and 1 minus xi square. And if you add up all these 3 shape functions, n1 plus n2 plus n3, that is exactly equal to 1. And let us derive the same shape functions by the generalized coordinate method. X of xi is a naught plus a1 xi plus a2 xi square, and at xi of plus 1 you have x1, that is a naught plus a1 plus a2. Xi of minus 1 is x2, a naught minus a1 plus a2, and xi of 0, it is just simply a naught, that is x3. So, if you solve these 3 equations, once again we get that n1 is xi times xi plus 1 by 2, n2 is xi times xi minus 1 by 2 and n3 is 1 minus xi square. See, these are exactly the same shape functions that we got from the Lagrange method. So, we actually should notice that all these are Lagrange elements, and we have only one dimension. So, we do not see the other dimension, but we can imagine this as a Lagrange element. And now let us follow a slightly different method, which is called as a serendipity method. Actually, serendipity is a statistical term, and it is actually accidental discovery, like the literal meaning is serendipity discovery is accidental discovery, like just by chance we have discovered this method or this procedure. And this method of deriving the shape functions for higher order elements is we start with the shape functions for a lower order element and then go on applying some corrections to get the shape functions for higher order elements. Okay. Now, let us start with this 2 node bar element. Our n1 was 1 plus xi by 2 and n2 is 1 minus xi by 2, and here the subscript refers to the node number 1 and 2 and the superscript refers to the number of nodes in the element. For 2 node bar element, 1 plus xi by 2 and 1 minus xi by 2. And now in this element let us introduce a node at xi of 0, that is the node 3. And then we have a problem, because these two shape functions, they do not become 0 at node 3, they become half. So, how do we make them 0 at node 3? And we notice that at node 3 n3 is 1. So, we can just simply write this, the shape function for 3 node bar element as n1 for 2 node bar element minus n3 by 2. Okay. And so, we can do the correction like this: n1 for the 3 node bar element is n1 for the 2 node bar element minus n3 by 2, that is 1 plus xi by 2 minus 1 minus xi square by 2, and that comes to xi times xi plus 1 by 2. Similarly, the n2 for the 3 node bar element is n2 for the 2 node bar element minus n3 by 2, that is xi times xi minus 1 by 2. So, once again we see that these shape functions that we got by the serendipity method are exactly the same as what we got from the Lagrange method or from the generalized coordinate method. So, actually the serendipity method gives us an advantage that we can use this method if the third node is present. If not, we will just work with the shape functions for the 2 node bar element. So, we can actually convert a lower order element into higher order element by doing this correction. Okay. And as and when needed, we can correct them. And so, in the program we can have both 2 node bar elements and 3 node bar elements, and then if necessary 4 and 5 node bar elements, and we can successively apply these corrections for getting the shape functions for higher order elements. So, we do not really need to invent a new method for getting the shape functions for the higher order elements. And the procedure that we have developed for one dimensional elements can also be extended to 2 dimensions. Now, let us consider a 4 node quadrilateral, and this is a typical Lagrange element, because we have the same number of nodes in each direction, and both along the horizontal direction, vertical direction. So, let us define node 1 in quadrant 1, that is 1 and 1. At node 2 in the second quadrant, xi is minus 1 and eta is plus 1. The node 3 is in the negative quadrant, minus 1 minus 1. Node 4 is in the fourth quadrant, xi of plus 1 and eta of minus 1. So, we can use the Lagrange procedure for getting the shape functions. So, n1 we can get it as a function in terms of xi multiplied by a function in eta to get the n1 of xi eta. So, in the so these are the shape functions that we already derived for the bar elements. At node 1, that is xi of plus 1, our shape function is 1 plus xi by 2. At node 2, at xi of minus 1, we have 1 minus xi by 2, and by extending the same procedure for eta direction, we have the shape functions 1 plus eta by 2 at eta of plus 1 and 1 minus eta by 2 at eta of minus 1. So, our n1 of xi eta is just simply 1 plus xi times 1 plus eta by 4, and n2 of xi eta is 1 minus xi times 1 plus eta by 4, and n3 is 1 minus xi times 1 minus eta by 4, and n4 is 1 plus xi times 1 minus eta by 4. Okay. So, these are the shape functions that we can directly write based on our Lagrange procedure, and we can also apply the generalized coordinate method and we will see that we get the same values. Okay, and the shape in the generalized coordinate method, the displacement function u of xi eta we can write as alpha naught plus alpha 1 xi plus alpha 2 eta plus alpha 3 xi eta, right. And by substituting xi and eta of 1 or minus 1, and we get the u1, u2, u3, u4 at node 1 our xi is 1 and eta is 1, and at node 3 xi is minus 1 and eta is minus 1, and so on. We can substitute all these values and get 4 simultaneous equations, so that we can get the 4 constants alpha naught, alpha 1, alpha 2, alpha 3. These are the generalized coordinates. Then once you substitute and simplify, we get our n1 as 1 plus xi times 1 plus eta by 4, n2 is 1 plus sorry, I think it is I think I am making too many mistakes. 1 minus so our n2 is 1 minus xi times 1 plus eta by 4, and n3 is 1 minus xi 1 minus eta by 4, and so on. And once again we get the same shape functions as we got from the generalized coordinate method, but then it is not real surprise because this is a pure Lagrange element. So whether you use a generalized coordinate method or Lagrange method, we will get the same shape functions. So I think that is the end of my lecture today, and if you have any questions, please send an email to Prof. KRG. So please do listen to all the lectures before you go for listening to the next lecture, because all of them are in a sequence. If you miss any sequence, then it is difficult for you to understand. So thank you very much. We will meet in the next class.